Look closely at a single drop of water. It appears completely still, but inside that tiny sphere is a densely populated, active microscopic universe. The strict physical rules governing those invisible particles are the exact same mechanics that allow our cells to process oxygen and our oceans to regulate the climate. This unseen movement is the functional baseline for nearly every major exchange of nutrients and energy on Earth. When you stir cream into your morning coffee, it looks like the two liquids simply merge into one. But there is a distinct structural difference between a casual mixture and the engineering of a true chemical solution. A solution occurs only when one substance integrates into another so completely that it vanishes from sight, without changing the original chemical identity of either part. This specific, balanced partnership is what dictates the physical limits of every liquid on our planet. Creating a solution requires two mechanical components, a liquid medium and a raw material ready to be broken down. The liquid doing the dissolving is the solvent. The substance disappearing into it is the solute. The solvent molecules surround the solid material, forcing continuous physical collisions until the solute is pulled apart and distributed into a uniform mixture. Mastering this specific solute-solvent interaction is how we engineer everything from life-saving medical drips to high-density industrial batteries. In its initial, unsaturated state, a solvent has plenty of room to absorb incoming particles, but that capacity is not infinite. We can see researchers measuring these exact boundaries on this chromatography plate, where chemical components separate based on their inability to stay dissolved. Saturation occurs at the precise moment a liquid reaches its maximum mathematical capacity and refuses to accept a single additional particle. At this point, the liquid has reached the strict boundary of its natural physical equilibrium. To push past this limit, chemists add energy. By heating the liquid, the molecules move faster and create more physical space for incoming solute particles to occupy. This creates an overloaded state called supersaturation, a condition where a liquid holds more dissolved material than the laws of physics normally allow. Because it is forced into this unnatural state, the system is highly unstable. A single vibration or the presence of a tiny contaminant can instantly break the delicate balance. The moment that fragile state is disrupted, the excess material snaps back into a solid through a rapid, total chain reaction. This crystallization is a demonstration of how systems return to a state of order once they are pushed past their natural physical limits. These identical rules of capacity govern the massive natural systems in the ocean. The entire sea functions as one giant, continuous chemical solution. The strict balance of salt dissolved in these waves allows complex marine life to survive without the water ever hitting toxic saturation levels. Your bloodstream acts as a solvent network, keeping medicines and nutrients dissolved so they can be safely transported through your veins. Whether in the deep ocean or in human biology, life depends on these fluids perfectly managing their chemical capacity. Next time you look at a glass of water, remember you aren't looking at empty space, but at a complex, active harmony of particles. To continue exploring how these physical rules shape the world around us, subscribe to the channel.